Okay, so in this video, we're going to learn about the last step to making Lewis structures, which is adding formal charges. So we're going to add some style and chemistry. We're going to get some business formal going on here. All right, so this is what formal charges look like when you apply them to molecules. You'll see these numbers on atoms, and you'll see that each of them have a designated positive or negative charge, or maybe even zeros. And these numbers here are going to dictate whether or not you should put a double or triple bond or single bond between atoms when you're sharing electrons, and what structure is best when you have two structures that both look correct. So the last step to drawing Lewis structures that we didn't learn in the last video is to check your work by drawing formal charges. This is the best way to make sure that you got your Lewis structure right. If your formal charges work out and you fulfilled the octet rule on everything and you have the total electron count right, you've done it right. So let's talk about what formal charge is. So this is the definition of formal charge here. It is the number of valence electrons that an atom wants. This is based on the periodic table. Subtracted from the number of valence electrons that it currently has. Okay. So let's look at a quick example here let's look at our carbon structure that we drew. 1, 2, 3, 4, 5, 6, 7, 8. Okay. We had determined that we need to have an octet on all of our atoms, so we had said we could do either one of two structures. We could draw it like this, or we could do it like this. These both fulfill the octet rules, fulfill octet on all atoms, and they also have the correct number of electrons. Total E minus. But the box that we haven't checked yet is our formal charges. So let's go ahead and look at formal charges on here. Let's calculate these. So in order to find formal charge, we need to go to our periodic table. And our periodic table is going to tell us the number of valence electrons that an atom wants. So carbon, nitrogen, oxygen, fluorine. This is group 7A, 6A, 5A, or 15 if you want to look at it that way, 4A. So that could be 14, 15, 16, 17, or 4A, 5A, 6A, 7A. So what we're seeing here is that carbon wants 4 valence electrons around it. So it wants 4 total. 4. And our oxygens want 6. So we need to try to fulfill these as best we can. So we're going to calculate our formal charges. So formal charges only count valence electrons, not all of the shared electrons. So shared electrons are not necessarily valence electrons. We can see here in these structures that you see it here. Some of these electrons belong to the oxygen, other ones belong to the carbon. They are technically being shared. But we can say that these electrons here in this oxygen's electron shell are its valence. So I like to draw circles around my atoms. I don't know if this will help you. If it doesn't, completely ignore me right now. But I like to do this in order to determine current valence electrons. This is how I do things. And so it lets me see the valence electrons really easily when I draw circles like this. We can see that the oxygen right now has, oh, I drew this wrong. Sorry, if it has a double bond, it'll only have 2 lone pairs. Okay. So we can see the oxygen right now has 6 electrons. This carbon here has 4 valence electrons. And this oxygen has 6 valence electrons. Okay, Let's take a look at the other structure. Bum, 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 bum. I'm going to draw my circles again. Circles and circles. We can see around our oxygen with the triple bond that it has 5 valence electrons around it. Our carbon has 4 valence electrons. Now keep in mind, every single one of these atoms still has a full octet because that includes shared electrons that are in the bonds, but our valence electrons do not include shared electrons. Our oxygen over here has 7 valence electrons. So let's look at the formal charges of these structures now. So for the first one, let's calculate the formal charge on this atom. The number of valence electrons it wants from the periodic table. So for oxygen, that's 6. It wants 6 minus the number of valence electrons it has, which is here, 6. So the formal charge on this one is 0. For carbon, it wants 4. We can see that here from the periodic table. We're going to subtract that from what it currently has, which is also 4. So good news. All right. And then the next one, it wants 6. That's from the periodic table here. And it has 6. So the formal charge for this one is 0. So all of those atoms have 0 formal charge on it. Let's look at the next structure. So for oxygen, with the triple bond, oxygen wants 6 electrons. It currently has 5. So the formal charge on this one is a positive 1. Carbon wants 4 from the periodic table. It has 4. It's still 0. Oxygen wants 6 from the periodic table. It has 7. So that gives it a charge of negative 1. It makes sense if you think about it. It has 1 extra electron. Electrons are negatively charged. So if you have 1 more negative charge, it's going to be a minus 1. Whereas the other way around, if you have 1 less negative charge, you're going to have a positive charge on it. So we have 2 structures here. One with a formal charge of 0, 0, and 0. Another one with a formal charge of plus 1 and a formal charge of minus 1. That one has a 0. One of these structures is definitely different from the other based on these formal charges, and one of them is definitely better than the other. So when you calculate formal charges, you want them to be as close to 0 as possible. So based on this rule, that means that this structure is the best structure. It's the one that's going to win out. And you can see it pictured here. So you might be wondering, why do we only look at the valence electrons in the Lewis structures when we're trying to determine formal charge? This is important because valence electrons are the ones in the outer shells. Remember, that's the definition of a valence electron. So carbon and oxygen have more than 6 and 4 electrons. They have these inner electrons here. These are also electrons here. But they don't participate in bonding. So valence electrons are the only ones that participate in bonding. Only electrons that participate in chemical bonding. And when we're looking at structures, we're looking at all these chemical bonds. So it makes sense that we aren't drawing the center atoms because they aren't reacting. They stay with their atom. They aren't moving around. So these guys don't move. They stay situated with the atom that they're attached to. So only the valence electrons are the ones that are doing the reacting and moving around and whatnot. So that's the only ones that we draw in our Lewis structures. We don't draw those inner 2 electrons. So to reiterate what we went through, remember that when you have a structure like this one that we looked at, your lone pairs, these guys right here, they contribute 2 valence electrons, whereas these bonds right here, they only contribute 1, because we're like kind of cutting them in half and saying that two of these electrons belong to one atom and two of these electrons belong to the other one. So I just wanted to make this distinction because students often get this confused. So please make sure that you don't get confused with shared electrons that contribute to the octet versus electrons that we're designating as valence electrons that are not contributing, or sorry, that belong specifically to that atom, okay? So formal charges on atoms don't always all equal 0. We want to try to get them to 0 if we can, but sometimes that's not always possible. So the general idea is for formal charges to be as low as possible as you can get them, and that's going to be the best structure. So here's an example of SO4 2 minus. This is a polyatomic ion that we learned about, but this structure is a molecular compound that is within an ionic compound, so that's really confusing. But you can see here that this has multiple structures that are correct. We've got 4 structures here that all fulfill the octet rule. Octet rules. And they all have the correct amount of electrons, of total electrons. But if you see here, they all have different formal charges. So we've got one structure where all of the oxygens have -1 charges on it and the sulfur has a +2. We've got one here where we're reducing the oxygen negative charges and then reducing them even more and even more. So the structure here that's going to be the best is the one with the lowest formal charge overall. So definitely not this one and definitely not this one. These two here are equivalent because we have a -1 and a -1 and a -1 and a -1. So either of these is okay for now. We're going to learn which one of these structures is actually better in just a sec. Okay, so now it's your turn. See if you can draw the best Lewis structure for this NO2 minus molecule, okay? You're going to apply everything that you learned from the last video in order to make the structure and determine how many bonds are on it, how many electrons are on it, if you should move some of those electrons into double or triple bonds in order to get what you want. And then I want you to place formal charges on the molecule. You can use this periodic table here to figure out what your formal charges are and see if you can get them as close to 0 as you can. Let's take a look at how to solve this problem. So the first things first is that we need to find our central molecule. If we look here, nitrogen, oxygen. Nitrogen is less electronegative because it's further away from fluorine in this case. That's an easy way to remember it. We've got 2 oxygens, so I'm just going to do this. Now we need to calculate our total electrons. So nitrogen is in group 5, it's going to contribute 5. Oxygen is in 6, it's going to contribute 6 at 6, and this is going to add an extra 1. So add all these together. We end up with 18 electrons, 18 total electrons. So we're going to place these around the structure. Right now we have 1, 2, 3, 4 electrons already on the structure. So I'm going to take those away. It's going to leave us with 14 electrons to place. So I'm going to go ahead and start on the exterior atoms, work my way in. So 2, 4, 6, 8, 10, 12, 14. So we've got to go to the center atom, 14. That's where those electrons go. Okay. Now what we want to do is make sure we've got an octet on all of our atoms, and we can put electrons into double or triple bonds if we need in order to fix that. So I've drawn my structure down here again so that we can look at everything. This one fulfills the octet rule. This one fills the octet rule. This says 1, 2, 3, 4, 5, 6. So it does not fulfill the octet rule. We need to fix that. So you can choose electrons from either oxygen. It doesn't matter. We're going to move them into a double bond here. in order to give everything a full octet. Okay. Oh, sorry. Okay. So this is what our structure would look like if we put all of the electrons on it and we fulfill the octet rule. So let's check our formal charges now. So for formal charge, oxygen wants 6. In this case, it has 7. Let me draw my circles to help you see that. It's only got 1 here. So it's got 7. So this one is a -1. Nitrogen wants 5. It has 2, 3, 4, 5. It's pretty happy at 0. Oxygen wants 6. It has 2, 4, 6, 0. Okay. So what we've got here is a formal charge of -1 on our oxygen and a charge of 0 on our nitrogen and a charge of 0 on our oxygen. So the question is, can we move electrons around and keep our octet, keep our total electron count, what it is, and still and lower our formal charge? So you might think about, can I put these here? You can even move electrons from the central atom over if you wanted. That's also a possibility. But what you're going to find is if you try to move those electrons, you're going to be breaking the octet rule. So we actually can't move any electrons here. This is as good as it gets, because if you moved electrons, say you did like this, you'd be breaking the octet rule because nitrogen would have 2, 4, 6, 8, 10 electrons around it, so we can't do that. So this is the best structure. It is the only structure that will work and fulfill all of these things. The last thing I want to talk about is that scenario that we saw with our SO4 2- molecule. When there are two best structures, there are two structures that have good formal charges on both of the atoms, but we don't know which one is best. So there is going to be a right and wrong. And the way to determine this is that the more negative charge goes on the more electronegative atom. This makes sense if you think about it. So we'll take a look at our OCN- molecule here. If we look, this is our electron density map. You can see that one of these atoms pulls electrons to it more. So it makes sense that the negative charges should be on the more electronegative atom because it's going to pull harder on the electrons. So that's where we're going to place them. Let's take a look at all of the correct iterations of this molecule. So I've drawn all of these here for you. You can see each structure of OCN. Every single one of these fulfills the octet rule. Octet. And it also has the correct total electrons. So the only way we can distinguish which structure is best is by using formal charges. So we're going to do that. So on our periodic table, we've got carbon, nitrogen, oxygen, fluorine. So we've got 4, 5, 6, 7. So oxygen wants 6. In this case, we're going to look at each one. It has 6 here, so its formal charge is 0. Here, it has 7, so that's a -1. And here, oh, this is wrong. There should not be anything there. Do that wrong. It has 5. So in this case, it's a +1. Let's take a look at carbon. Carbon, for all of these, I'm just going to tell you, it has a formal charge of 0 on all of them. It has 4 valence electrons on every structure. It wants 4 electrons, so it's 0. It's the same. Now let's take a look at nitrogen. Sorry, there we go. So nitrogen it wants 5. It has 2, 4, 6. It's got a charge of -1. This nitrogen here, it wants 5. They all want 5. Sorry, that's the same. It has 5, so it's 0. One's 5. This one has 7. Oof. Okay, so it's got a charge of -2 on it. All right, so we want to get these charges as close to 0 as possible. That's going to be the best structure. So off the bat already, we can see that this structure is out because it's got a +1 and a -2. Those are really far from 0, whereas all of our other structures have 2 zeros and a -1. So we've got 2 zeros and a -1, 2 zeros and a -1. So these structures are definitely better than that other one. So definitely not this one. Okay. Now we need to figure out which one is best, the one with the 2 double bonds or the one with a single bond and the triple bond. And the way we do that is by making sure that the more negative charge is on the more electronegative atom. So which one is more electronegative, oxygen or nitrogen? That's the one that we're going to want the negative charge on. So in this case, that's oxygen here. It's more electronegative right here. So that means that this is the correct structure. This is the best structure because here it has our negative charge on our nitrogen and we want the more negative charge on the more electronegative atom. So that's how we choose this. We can go back to our sulfur example as well and determine that too. So on the periodic table, oxygen is actually directly above sulfur, so they have the same valence electrons. So that means, again, that oxygen is more electronegative. So oxygen is going to want that negative charge more than the sulfur. So out of these two structures, which one would be best? You see here that sulfur has the 0, and we've got the 2 minuses on the oxygens, whereas here we've got an oxygen minus and a sulfur minus. We don't want this because oxygen is more electronegative. It pulls harder. So if we can have the minus charges on the oxygen, that's going to be best. So this is the best structure out of all of these. So that's all I have for you today on formal charges.